In the name of Almighty God, I'm Asa Sankash, and today I want to talk about gravitational redshift of broadband relativistic quantum photons. It was written by Alessio Laponi and his colleagues from the Naples, Italy, and also Fachhochschule Centrum from Germany was written by the aid of the researcher groups. We employ linearized quantum gravity to study gravitational redshift of photons in the context of relativistics and quantum physics, where photons interact in flat spacetime with a classical massive body via gravitation exchange. We find that gravitational redshift, as predicted by general relativity, occurs only in the case of the localized photons with a well-defined momentum that they interact with a classical source of gravitation. On the contrary, photons initially prepared in states with non-classical features such as quantum coherence in the position's degrees of freedom. With this novel find redshift in general, our work not only shows the gravitational redshifts can be found in flat spacetime as a consequence of the interaction of quantum fields, but it also challenged the robustness of one of the most important predictions of general relativity, furthermore indicating that the deviations from the theory can already be observed at low energies using highly non-classical photonic states. Gravity is the first fundamental force of nature to have been formalized in modern science. The classical theory of general relativity accurately described the vast majority of gravitational phenomena at the macroscopic scales. Quantum mechanics, on the other hand, is the pillar supporting our understanding of physical phenomena at small scales. The development of quantum field theory has led to the unification of the other three fundamental forces, for example, electromagnetic, weak and strong force, into a coherent picture. Nevertheless, it has been difficult so far to include general relativity in the picture. This disparity leaves open a foundation a question: is gravity fundamentally classic, or does it have an underlying quantum nature? In the past decades, huge efforts have been dedicated to answer this question, ranging from proposal of a theory of quantum gravity, stochastic gravity models, and entropy-based approach to semi-classical theories for collapse models and quantum classic frameworks. Furthermore, many experiments have lately been proposed not only to improve our understanding of physics at the overlap of general relativity and the quantum mechanics, but also to test the very quantum nature of gravity itself. The development of a unified theory of nature can greatly benefit from the simpler step of understanding gravitational or quantum mechanical phenomena through the lens of the quantum information. This approach has developed in a multifaceted field that includes frameworks such as relativistic quantum information and analogous gravity. Gravitational redshift is one of the paradigmatic predictions of general relativity with significant experimental validation. It occurs when a photon is emitted with a given frequency and is detected with a different frequency after traveling in curved spacetime. Gravitational redshift is well understood classically, for example, by taking into account the different flow of time for observers located at different points in a curved spacetime. On the contrary, this effect is not understood in the context of the quantum physics. Initial work in this direction has developed a simple quantum optical model of gravitational redshift affecting photonic quantum states, and further work has improved the understanding of photonic wave packets propagating in the curved spacetime. To date, a coherent picture of gravitational redshift of photonic wave packets remains outstanding. In this work, we study gravitational redshift in the context of relativistics and quantum physics. More precisely, we ask the following: Do photons always experience gravitational redshift as predicted by general relativity? To answer these questions, we first define redshift of quantum wave packet in the context of quantum field theory in the flat spacetime. We then employ the framework of linearized quantum gravity, where photons interact via gravation exchange with a massive body that is modeled as localized excitation of a massive scalar field. In this context, the weak interaction of the field of the interest with gravity naturally occurs in the flat spacetime, thus obviating the need to employ quantum field theories in curved spacetime. This allows us to compare our predictions to those obtained classically by providing a qualitative analysis of phenomena of interest without a loss of generality. Linearized gravity is employed to describe scenarios where curvature is weak and deviation from flat spacetime are small. The metric G micro nu has the expression G micro nu is equal to eta micro nu plus epsilon h micro nu, where epsilon is too much less than 1 is a control parameter, and eta nu micro nu is equal to diagonal minus 1 1 1 1 is the Minkowski metric. Einstein's field equations in a vacuum read h micro nu minus 1 divided by 2 h micro nu h is equal to gamma micro nu is equal to 0, which implies that the tensor perturbation gamma micro nu is equal h micro nu minus 1 divided by 2 h micro nu h propagates as a wave in a vacuum. Einstein equations contain unphysical degrees of freedom, which we remove by imposing the harmonic gauge delta micro gamma micro nu is equal to 0. This allows us to start from the Einstein-Hilbert action and derive the Lagrangian density Lg is equal to minus 1 divided by 4 delta p gamma micro nu delta rho gamma to the power of micro nu minus 1 divided by 2 delta p rho gamma to the power of delta rho gamma, where gamma is equal to tr gamma nu micro. See reference 52. The variables gamma and gamma micro nu are treated as independent degrees of freedom for which gamma micro is equal to gamma is equal to 0. We now promote gamma micro and gamma to operators following standard procedures for canonical quantization. We obtain a gamma micro is equal to square root hpg and integral d to the power d to the power of 3 k and p micro nu k e to the power of I k x plus hc, where the third derivative k is equal to third derivative k divided by square root 2p to the power of 3 to omega k. Omega k is equal to absolute k for the massless gravitation, and p micro nu and p are interpreted as the annihilation operators of free gravitation with spin 2 and 0 respectively. They satisfy the commutation relations. While all others vanish, the normal ordered free Hamiltonian of free gravitations read Hamiltonian 0 g is equal to 1 divided by 2 integral d3 k absolute k p micro nu k p micro nu k minus 2 p k p k. Within the framework of perturbation theory, it is convenient to employ the free field expansions for the photonic field and the source field respectively, where x to the power of micro is equal to tx, k to the power of micro is equal to omega k, and x to the power of micro k micro is equal to minus omega k t plus x k. Note that k to the power of 0 is equal to absolute k for the photonic field phi, while k to the power of 0 is equal to omega k is equal to square root m to the power of 2 plus absolute k to the power of 2 for the massive field phi. Here, the sharp momentum operators satisfy the conical commutation relations such as I coupling is equal to C coupling is equal to delta to the power of 3 minus coupling, while all others vanish. The free Hamiltonian for the uncoupled field phi and phi 15, read Hamiltonian 0 and phi is equal to integral d to the power of 3 ka, absolute ka, I ka, and I ka. And Hamiltonian 0 is equal to integral d to the power of 3 ka omega ka c ka respectively. The interaction between the gravitation field and all other field is given by the Hamiltonian ka of 1 I ka is equal to 1 divided by 2 integral d to the power of 3 gamma micro nu minus 1 divided by 2 gamma eta nu micro no and micro, which is given T micro nu ka, where ka is equal to phi for the photon field phi and the source field of phi respectively 52 and 53 here. T micro nu is equal to delta micro phi delta nu phi minus 1 divided by 2 eta micro nu delta to the power of rho phi delta rho phi is the stress energy tensor for the photons, and T micro nu is equal to micro nu and zeta micro nu delta nu minus 1 divided by 2 eta micro nu delta to the power of rho and phi delta rho and phi prime plus m to the power of 2 multiplied by m to the power of phi to the power of 2 is one of the source. We use the notation t micro nu to the power of ka and t ka to the power of micro nu are as needed. The stress and energy tensors are normal order to avoid spurious divergences and are evaluated at t0 is equal to 0. Note that this perturbation approach requires the interaction between the fields to be small compared to the bare energy scales. This condition is standard in perturbative approach to quantum field theory, where the back reaction of the photons on the background spacetime is negligible, and we work in the weak field limit. For example, photon gravitation dynamics occurs far enough from the planet. The time evolution operator for the whole system is given by the UAT is equal to e to the power minus I Hamiltonian t, where Hamiltonian is equal to Hamiltonian 0 plus Hamiltonian 1 is the full Hamiltonian. Hamiltonian 0 is the total free Hamiltonian, and Hamiltonian I is equal to Hamiltonian alpha, and Hamiltonian I 0 is the total interaction Hamiltonian. To process, we need to determine initial states for the whole system. First, we assume no correlations between the different subsectors, for example, gravitation, photons, source field, in order to uniquely attribute any effects to the interaction alone. We leave the initial reduced states of the photons to be specified when necessary. Next, we focus on the source in order to model a localized massive quantum object characterized by the special features which we will call planet. We consider the extended operator C is equal to integral d to the power of 3 ka f ka c ka, where C and C prime is equal to integral d to the power of t ka absolute f ka to the power of 2 is equal to 1. Here f is the distribution of the momentum of excitations which is peaked around Ka with variances sigma. The special profile of the source excitation is given by the f x is equal to 2p to the power minus 3 and integral d to the power of 3 ka f ka e to the power minus ka ix, which gives us their spatial density rho x is equal to absolute fx to the power of 2 normalized by the integral d to the power of 3x. Rho x is equal to 1 since the momentum distribution f has natural wide sigma. The spatial amplitude f has a natural wide r is equal to 1 divided by sigma. Finally, the source will be assumed to be static. For example, chi0 is equal to 0, which implies that we will work in the regime lambda c divided by r is less than 1, where lambda c is equal to 1 divided by m is the Compton wavelength of the excitation, and omega k is equal to m. The source field is initially found in a coherent state defined by the c omega 0 is equal to zeta where the d Zeta is equal to e to the power minus zeta prime c minus zeta c is a displacement operator that satisfies the zeta c d is equal to c epsilon z star when absolute zeta is greater than 1. The expectation value t micro nu zeta is equal to uh, this expression of the stress energy tensor and satisfies the approximations where we have identified m is equal to absolute zeta is to the power of 2m as the total mass of the planet. The total energy of the planet is given to lowest order by 0 phi is equal to epsilon Hamiltonian 0 is equal to m as expected to the stress energy tensor correctly models a static object with energy density. We finally consider the state of the gravitations, which here are excitations of a quantum field in a flat spacetime. We don't wish to impose an ad hoc initial states, sometimes done in the literature 60 and 62. Instead, gravitations appear only as a consequence of the presence of the planet, since the energy carried by the photons is negligible. This motivates us to assume that there are no initial gravitations and thus their initial states is such as absolute 0 Ag belongs to Hamilton energy defined by the B ka 0 Ag is equal to 0 for all ka. The total initial states of the interest is therefore the zeta 0 is equal to zeta g multiplied by these expressions. A localized photon is an excitation of the photonic field that is created at time t is equal to 0 by the operator, where I f a chi 0 x 0 I f a chi 0 x 0 is equal to integral d3 multiplied by ca f a chi 0 star ca multiplied by e to the power minus I ca x 0. We now move on to compute the effect of interest. We focus first on frequency shift, called redshift for simplicity as a general phenomenon, and specialize to gravitational redshift later. The claim that redshift is a change omega tends to omega prime is equal to 1 plus z multiplied by omega, and the sharp frequency omega is equal to absolute K of the photon, where z is redshift is not exportable directly to the current setting since photons have finite bandwidth. Therefore, we refine the definition of redshift following intuition developed by a quantum optical approach to model the effects of classical gravitational redshift within a relativistic quantum mechanical context. The scheme is depicted in the box above. The next step is to answer the following two fundamental questions regarding the first question is under which conditions is redshift present in a photonic state. The next questions would be how does quantum coherence in the states affect the occurrence of redshift? We answer the first question via the straightforward computation produced in full in the supplement material. Let us assume that beta is equal to zeta 0, zeta lambda 0 is an orthonormal basis of photonic states at t is equal to 0, where lambda is a set of the appropriate indices defining the orthogonal space to the initial states of interest. We can then write the phi t is equal to e to the power minus I zeta is 0 Hamiltonian zeta 0 t and multiplied by 1 plus delta 0 t for phi t in a reference 8, where delta is absolute delta 0 t is equal to max sigma lambda lambda prime delta lambda lambda prime t phi 0 Hamiltonian phi lambda 0, and the delta lambda lambda probability can be obtained recursively via an infinite series. We therefore see that a sufficient condition for redshift to occur is that the initial state absolute zeta is an effective eigenstate of the Hamiltonian H with the eigenenergy 0, and thus delta 0 t is equal to 0 and absolute Phi is equal to 1 as required by reference 7. We now turn to the question of the interplay of quantum coherence and redshift, a question of interest for quantum mechanical models of gravitational effects as well as test gravitating quantum matters. We introduce generic states where sigma n absolute to Cn to the power of 2 is equal to 1, and we assume that each orthogonal states witness redshift via absolute Cn t is equal to e to the power of I multiplied by 1 plus zn absolute cos 0 n t and also multiplied by zn. Such states can be implemented, for example, as frequency comb states where each peak is sharp and well separated from all others. If only one photon is presented, it can also model a photon in a special superposition of different locations. In general, the state contains quantum decoherence if there are at least two non-zero coefficients. This can be seen by using the relative entropy of coherence, and is the von Neumann entropy of a state rho, and rho diagonal is the state obtained from the rho by removing all of the diagonal terms. In our case, we have CRS E is equal to minus sigma absolute C n to the power of 2 ln absolute C n to the power of 2 is not equal to 0, which proves this, that the state has coherence in general. So note that the effective interaction Hamiltonian is a collection of beam splitters and phase rotations. The derivation of requires that the planet is initially found in a coherent state with a large number of excitations, for example, large mass, which is a good model for a classical object. In such case, the effective evolution of the photon is unitary and no loss of information to gravitational degrees of freedom occurs. The main expressions and can therefore be used to obtain the desired effect for any classical source. We are finally able to prove our claim regarding gravitational redshift. We compute an explicit expression for reference 8 in the specific case of classical planet found at a large distance from the photon. See figure 1, a single photon with the quantum states absolute 1 epoch 0 x0 is initially localized around x0 and travels away from the planet, while the planet can effectively be approximated as a point-like object. For example, rho x is equal to delta to the power of 3x. We find that these expressions in equation 14 and gamma rho is the form factor found in classical case. See the box below. We can then identify the average redshift. Z is equal to minus RS divided by 2 absolute x0 gamma rho, which coincides with the redshift based on the reference 16 obtained classically irrespectively of the shape of the photon. We stress that it is possible to obtain the result only when the photon has a well-defined momentum. For example, any correction to the effects are subdominant to the small bandwidth to peak parameter sigma divided by absolute chi0. We finally employ the reference 14, which states of the form reference 10 in the case of the relativistic planet for which the Zn is less than 1. Thus, the wavelengths chi0 n are tightly distributed around the average wavelength absolute chi0 via the distributions absolute chi0 n is equal to 1 minus Rs divided by 2 absolute x0 n multiplied by gamma p absolute chi0 when the 0 divided by sigma is less than 1. In such case, we find these expressions when delta nm is equal to 1 divided by x0 n minus 1 divided by absolute x0 m here absolute EFET is not equal to 1 in the general, and therefore the single photon scenario reduces the expected one from the general relativity only if the source is a classical distant planet, while the photon is localized along the trajectory of propagations, which effectively no measurable quantum coherence in its state. To conclude, we have introduced a notation of redshift for a broadband quantum photons and have determined the criterion by which its presence is certified. We have shown that the redshift occurs almost exclusively when the photon can be effectively modeled by a peak momentum distribution to lowest order in the bandwidth to peak frequency ratios even divided by absolute cause rule less than 1. We then employed the framework of linearized quantum gravity to prove that in such regime one recovers exactly the standard gravitational redshift as predicted by general relativity if the massive source of gravitational class curve. Crucially, we find that the photon doesn't, in general, witness as well-defined gravitational redshift when quantum coherence is present. Our work therefore provides a novel understanding of a key prediction of classical gravity whose limits can be tested in the satellite-based environment using current photonic quantum technologies. Our results complement ongoing efforts to understand the interplay of gravity and quantum mechanics, such as those that the proposed test of quantum field theory in curved spacetime at low energies 7071, as well as those that aim at demonstrating the quantum nature of gravity using entangled systems. Acknowledgements. We acknowledge Stefan Manischini and Andres Wolfgang Schell for their suggestions and comments, which provide invaluable to this work. AL is particularly thankful to Capozilio for useful discussions to improve the quality of this manuscript, as well as for supporting a long-term visit of to Forschung Centrum Jülich and etc. So thank you so much for watching my tutorial video until the end. If there is any simulation for this literature, you can find it from github.com/maxscript or github.com/kashi script or github.com/safroscript. Today is the 9th day of July 2026. Time is near noon.